First section is about rational exponents. And remember, rational, that word is just code for fractions. Rational exponents are fraction exponents, and we're going to work on simplifying some of those, and I'm going to show you how to do that using just manual techniques, and then I'm going to show you how your calculator can help you with some of these, and really, make some of it easier. But the manual techniques are important because sometimes when we go to simplify them, it doesn't work out to be a nice number. So it's like a decimal answer, and we want to be able to get an exact solution to that. So it's kind of like when we were simplifying square roots back in 100 with this, like the square root of 12 was a decimal, but we could reduce that down to get like 2 radical 3 out of it. It's going to be the same idea here with rational exponents and when we do radicals in the second section. So I'm just going to show you some techniques here, and some of them we've already used. So it's just going to be bringing that back up and putting it in a different context. So instructions would be to simplify the expression, and we'll just start with something fairly simple like a 49 to the 1/2 power. Okay, so there's a 1/2 exponent out of that. So it's the idea here is very similar to simplifying square roots. The 1/2 power we'll see is also a square root. Just it's out of, not that you have to know that to do this, but we're doing square roots here with the 1/2 power. The idea is still do the factor tree like we did with square roots, no matter what the fraction exponent is. So here we have 49, we know is 7 times 7. So this is really 7 squared to the 1/2 power. And then we can utilize our exponent rules that we know that anytime that there's an exponent outside of the parentheses, the rule is to multiply those together. So we take 7 squared to the 1/2. You say 1/2 times 2 would be 1. So that's 7 to the first power, which we know is 7. So that reduces down to be 7. Because it works out to be a nice number, your calculator could have done that problem. And the way to do that is just type in the 49 and raise it, the caret symbol just underneath clear, and then you just type in your 1/2, and it cranks out the 7 out of that. So if it works out to be a nice number, if this were 48 raised to the 1/2, it's a different game. We would know we would have to do the factor tree stuff out of that. So you can check these with the calculator first if you want to, and just see if it will work that for you. And if it comes out to be a decimal, I have to do the factor tree thing out of that. So that's kind of how I try to approach this, is look for ways to make it a little easier. Like 64 to the 1/2 is, I know from experience that that's 8 times 8, and 8 is 4 times 2, and 2 and 2. So I'm showing the factor tree method because it's going to be helpful when we don't get to use the calculator on it, because we got to simplify. But this time the calculator would have done this, but it's 2 to the 1, 2, 3, 4, 5, 6 power. So I did the factor tree for 64, and I got 6 2's. So that's 2 to the 6th power, and that's still to the 1/2 power. And then we use that same rule that we multiply those together, and that would be 2 to the 3rd power, which 2 to the 3rd power is 2 times 2 times 2, which is 8. And again, your calculator would have done that one. So, sometimes I think showing the other method is going to be helpful when we do some that don't work out so nice. It's also going to be helpful when we start doing some equations later on, that you need to be able to kind of think about numbers in that way, because when they start throwing X's in there, it makes it tougher out of that. Let's take a 1/3 power, just change it up. So example C, let's do negative 27 to the 1/3 power. So if I think about that, I'm going to try it with my calculator, and I'm going to type it in negative 27 raised to the 1/3. And I get back -3 as the answer, which is true. The reason that is because this is -3 times 9, and 9 would be -3 times -3. So that's really -3 to the third, and then to the 1/3. This is the non-calculator way of thinking about that problem. And then you multiply those two together, and we get -3 to the first, which is just -3. So again, you could check it with your calculator first to see if it'll do it. And if it does, that's fine. You can get your answer that way. But using the factor tree is going to help us later on. So being able to do that is going to help us later on when we start doing some equations and things where we've got exponents and variables involved. So it's kind of helpful to get to there. Let's try this one. 16 to the 1/4. So just some different numbers here. If I check it with my calculator, 16 raised to the 1 divided by 4, I get a 2 out of that, which, that's a great answer. It works. Why is that the answer? Well, if you do the factor tree, we know 16 is 4 times 4, 2 and 2, 2 and 2. So that's really 2 to the 4th power to the 1/4. And then when you multiply those two together, that's how you get the 2. That's the non-calculator way of doing that. And again, I hate to keep beating a dead horse there, but it is going to be helpful later on, maybe when we got some stuff to do with some equations, got variables involved. All right. So example E here. Let's do 64 to the, we've done 64 to the 1/2. Let's do 64 to the 1/6. That's just a different fraction exponent. That's all that is. And we can work that out. I know that 64 is 8 times 8 already. I know it's 4 times 2, 2 and 2. We've already done this number. So we know that it's actually 2 to the 6th power to the 1/6. And there's 2. And if you did that with your calculators, 64 raised to the 1 divided by 6, it's going to get you that 2, just like, doing it by hand would. But again, doing the factor tree stuff can really be helpful as we move into some harder stuff later on. Okay. One thing that can come up here is if you had like a -64 to the 1/6, that problem, if you tried to do that with your calculator, if I typed in -64 raised to the 1/6, notice what it gives me. Mine gave me this complex number out of that, and that's telling us that this is a non-real solution out of that. Anytime that you're taking a negative number and raising it to where the denominator, if that denominator is even, you're going to get a complex solution. And in our case, for this particular course, anytime that happens, we're just going to say that this is not a real number. For this course, that's what they ask us to do. They say, okay, don't work it out if it turns out to be a complex solution. And the reason that that's complex is that has an even denominator on the fraction, and it's a negative number that we're doing that to. Okay. If it's a positive number and an even denominator, you're okay. It's not going to give you a complex number. If it's an odd denominator on the fraction, it's okay to have a negative in there. It's only if there's an even number in the bottom part of the fraction that you're going to put not a real number as the solution to that. Okay. So there's a problem that looks very similar to this problem, -64 to the 1/6. That they look almost like the exact same problem, but they're not, because of the parentheses not being in example G. The parentheses not being there tells us, oh, well, really what's happening, scroll, see better, is this is -1 times 64 to the 1/6. That's how you want to think about that. And I know that I can work that out already, that's -1 times 2, and then that answer would be -2. And again, if you could type that directly into your calculator, it works out, -64 raised to the 1/6. So a little calculator exercise on a lot of stuff tonight. All right. And then let's start changing up that numerator on that fraction. Every one of the fraction exponents we've had so far has had a 1 in the numerator. So let's start changing that up a little bit and see if we can see what's happening with those. And let's say we had something like 81 to the 3/4. Again, you can type that right in your calculator. This one does work out nice. But here's what's happening. If we take the 81 and break it down using the factor tree like we've done in the past, we end up with 3 to the 4th power to the 3/4 power. So this is what's happening. And then the rule is, okay, we'll multiply those two exponents together, and that will get you the result. Well, if I multiply those together, what's 4 times 3/4? It's 3. So I end up with 3 to the 3rd power, which is 27. And again, I could type that right into my calculator, 81 raised to the 3/4. And it works it out because it is a good number. If that were 80 to the 3/4, you can't do that. So you got to do a little bit of different work. So we'll get to something like that in just a little bit that aren't calculator friendly. Let's do another one that is still calculator friendly. 25 to the 3/2 power. So an improper fraction as the exponent. So still same rules though, as far as how it works out. You do the factor tree for 25. Not 2 and 5. 2 5s. What I meant to write there. So that's 5 squared. And that's 3/2 still. And then we multiply those two fractions together. And that's going to give us 5 to the 3rd power, which is 125. Again, you can type that directly into your calculator. 25 raised to the 3/2, and it's going to crank out 125. But where's that coming from? With exponents, that the rules, are the multiplying of the exponents there. That's what's happening. If you had, let's start kind of getting into those that don't work out maybe quite as nice. 12 to the, let's do 2/3. If I tried that with my calculator, I get a decimal out of that, which tells me, that doesn't work to do, give me an answer. That's not going to be what I want. So I'm going to work that out using the factor tree. So I've got a 12 is 6 times 2, and then 6 is 3 times 2. So it's really 2 squared and 3 to the 1st power raised to the 2/3. Well, if I'm going to simplify that a little bit, the rule is that I multiply this 2/3 times both of those. And that's going to give me 2 to the 4/3, and then 3 to the 2/3. So we end up with we call it simplifying, but it doesn't look simpler, does it? It looks bigger, but we're actually breaking those bases down a little bit there. So it's using a factor tree to break the base down to get it to its smallest terms. That's what we're trying to really simplify, is the base, not necessarily the entire problem. When it's not a pretty number with a particular base, or exponent that we have. Let's try this one and see what happens with it. Maybe 216 to the negative 2/3. 216 is a unique number. I think, we have 216 raised to the negative 2/3, and it gave me back a decimal. So that makes me think, well, maybe something's not quite right here. But we got to keep in mind that it's a negative exponent, and so that may have something to do with that fraction. So if we do the factor tree for 216, I don't know much about 216 other than, maybe 2 goes into it 108 times. So my factor tree, I'm going to start with 2 and 108. And then I know 108, I know something about it. It's 9 times 12. And then 9 is 3 and 3. 12 is 6 and 2. And then 6 is 3 and 2. So we get a lot of stuff there. We got 3 3s, so that's 3 to the 3rd power. And then there are 3 2s, so that's 2 to the 3rd power, to the negative 2/3. All of that's raised to the negative 2/3. So what we've done is taken 216 and broken it down as a factor, as its factorization for that. And then the rule is that you multiply those exponents together. And if I multiply negative 2/3 times 3, that's going to give me 3 to the negative 2 times 2 to the negative 2. Well, negative exponents, if you remember from the exponent rule stuff, well, that means, well, I've got to fix those and make them positive. So if I move that to the denominator, it changes that sign. So it'd be 1 over 3 squared times 1 over 2 squared. And we know what 3 squared is. It's 1 over 9. And then we know 2 squared is 4. So we'll get that. And then when we multiply those two fractions together, I wonder if that decimal that we got, if I hit 216 raised to the negative 2/3, hit math, enter, it's 1 over 36, which is the same thing. But how many of us have it memorized that 1 over 36 is 0.02 and then 7 repeating? Probably none of us. I don't have it memorized, even though I do that example quite a bit. I still don't have that memorized that that's what that is. Okay, so that's where using the factor trees can help you, especially when you got those negative exponents deals in there. Anytime you got a negative exponent, you got to figure, hey, there's going to be some sort of fraction involved to this. So the way I did that with the calculator to get it to give me the 1 over 36 is I did 216 raised to the negative 2/3. And then I hit math, which is underneath the green button, and then enter twice. And it'll change it, any decimal that you've got. If it can be changed to a fraction, it will change it to a fraction for you. Math, and then enter twice. So you get that answer and don't hit anything, just hit math, enter, and it'll change it to a fraction for you. If it is 1. If it's not 1, it won't do it. So there are scenarios where it can't change it. Kind of playing off of that idea of some of the exponent rules with the negatives and all that stuff that we've done here with multiplying those. We still use those. If they start throwing a problem that has some more operations in it to us. All right, so 18 to the 1/2 and 18 to the 7 over 2 and then 18 to the 3rd power. So we've got all of them have the same base, which is nice because that tells me, hey, I probably don't have to do much simplifying at the beginning. I'll just do it all at the end with the 18 if at all possible, or if necessary. It might not be necessary. So we got to remember exponent rules are when you multiply together. So that top part, they're multiplying together. What's the rule for exponents when you multiply? It's add. So we're adding 1/2 plus 7 over 2. So this is 18 to the 1/2 plus 7 over 2. And the bottom one hadn't changed any. So 1/2 plus 7/2 would be 8/2. 8 over 2 is 4. So if you struggle with that, do that addition of the fractions. Gives me a 4 exponent on the 18 up top. And then we now have a division problem. So I've done the multiplication that was up top. Now I've got a division problem to do. Since the bases are the same, I don't need to simplify them yet. I'm just going to go ahead and do that rule for exponents. Well, if the rule for multiplication was add, the rule of division has to be the opposite of that, which would be subtract. So it's going to be 18 to the 4 minus 3, which is 18 to the first power, which is just 18. And I end up not even having to do anything to simplify that. It worked out for me out of that. So sometimes they're going to throw some extra things in there, and the rational part of the exponents kind of sometimes goes away. Then let's look at one that didn't work out quite as nice. 100 to the 3 over 2 times 16 to the negative 3/4. So this one's weird because it has different bases on the two pieces, and they're multiplying together. So that tells me I can't just go ahead and do with anything with the exponent rules here with the two pieces, but I could try to work out each individual piece and then see if something happens. So that's what we're going to do with this, is we're going to try to break down the 100 to the 3 over 2, and then we'll work with the 16 to the negative 3/4 and see what happens with that. So I'm going to try to use my calculator, if it will, raise 100 to the 3 over 2 and see what I get. I get 1,000. That's nice. That's a good number. It's not a decimal. So this turns into 1,000. And then if I did 16 to the negative 3/4, that negative exponent tells me, hey, there might be a fraction involved. So after I type that in, 16 raised to the negative 3/4, it gave me a decimal. And if I hit math, enter, I think that one's going to turn into a fraction. It does. It turns into 1 over 8. All right. 16 raised to the negative 3/4 turns into 1 over 8. And then we can, that's just regular numbers now. It's 1,000 times 1/8. And I can do that math with, I'm going to do it without a calculator, but it's summertime. That's a 125. Works out to be 125. If we had done that without the calculator, with the factor tree methods, we know that 100 is 10 squared. So that could be 10 squared to the 3 over 2 times, and then 16 we know is 2 to the 3rd, or excuse me, 2 to the 4th power to the negative 3/4. And then that turns into 10 to the 3rd times 2 to the negative 3. And that is where those come from. Those are the exponents that turn into 1,000. 10 to the 3rd power is 1,000. 2 to the negative 3 would be 1 over 2 to the 3rd, which is 1/8. 2 to the 3rd power is 8. So that's how that works out. So it's just using some of these exponent rules that we should already know or be familiar with. May not be good at them yet, but this really starts making you practice them a lot. So calculator can be helpful on a lot of this stuff. So, I skipped a whole bunch of letters, didn't I? J. I'm going to go back and fix them because my OCD's killing me. It doesn't matter what they're called. But I had them lettered different on my notes there, and I had a few repetitive ones, and I thought I'd cut them out. Yeah, 5x. So we're going to throw some variables in there and see how that affects things. And again, it's still going to be exponent rules stuff. So when you throw the variables in there, you really got to know your exponent rules, because the calculator's not going to help you out with variables. That's where we run into problems. So here, the base that we're dealing with is an x on both of these, and it's multiplication. So the numbers that are in the front are just regular numbers, and we're just going to multiply them together out like normal. So 4 times 5 is 20. And then the x, the base, since we're multiplying, the rule is we add the exponent. So it's going to be 3/4 plus 2/5. And you could get a common denominator with those and work that out. I don't see any need in working that out that way. I mean, you got a calculator that can add 3/4 plus 2/5. And then I'm going to hit math, enter, and get that fraction exponent is 23 over 20. And we want to have that, leave it. You can't do anything with that because it's a variable. You can't simplify that in any way because it's a variable. It's x. If it were a number, then we'd try to do something with it. But we don't have a number for that, so we're just going to leave it that way. Okay, so any coefficient or number that's in front, you're just going to do the normal math with, and then do your exponents on your variables, the exponent rules that we've dealt with. Let's do this one. 5m to the 4/3 over n to the 2/3 in parentheses, and then squared on the outside, times, let's do another set of parentheses, m to the 4th over 8 n to the 5th, all to the 1/3. So this is really one that kind of adds up stuff here and gets going with a lot of different things. So it's got the exponent rules that we have to deal with. It's got coefficients that we have to deal with. It's got rational exponents involved that we're going to have to deal with and simplify if we possibly can. So first thing would be to just work each set of parentheses by itself first. They're one problem inside of another problem. So rule is, since there's a 2 on the outside, it multiplies to every exponent on the inside. So that 5 has a 1 exponent, and that's the one that most people forget, is to say, okay, I got to square that 5, which is 25. And then 2 times 4/3 would be m to the 8/3. And on the bottom, we got n to the 4/3. And so that's just taking 4/3 times 2 and hitting math, enter, get 8/3. And then we take 2/3 times 2, math, enter. And that's where I'm getting the 4/3. So I'm just multiplying those fractions times that 2. Okay, so we've done, well, everything we can do on the first piece. So now we got to work with the second one. And it's the same rule. We've got a 1/3 in parentheses with the 1/3 exponent outside. So that multiplies to every exponent on the inside. Even that 8 has a 1 exponent. And again, that's the one that most people forget. So we're taking 4 times 1/3 would be 4/3. 1/3 times 1 would be 8 to the 1/3. And then 1/3 times 5 would be 5/3. Once we've done that, we can start simplifying those pieces. Well, I see a number with a rational exponent, and anytime I see that, I look to see if there's another one that has that same base. This one has a base of an 8, but that's a 25 up there, so I can't do that. I can't. If that were an 8 to the 4th power on top, I could do subtraction or something with that. But because it's a different number, that means I need to just go ahead simplify 8 to the 1/3. And I think it works out with, nice, 8 raised to the 1/3. So I just check it with my calculator, and it does. It works out to be 2, because 8 is 2 to the 3rd power, and the 1/3 cancels out the 2. So, or cancels out the 3 there. So this is really now 25 m to the 8 over 3 over n to the 4/3 times m to the 4/3 over 2 n to the 5/3. So all I did was simplified that 8 there. That's all I did right there. Nothing, didn't do anything to anything else. So just trying to do one step at a time. All right. The next rule would say that you need to multiply. And when we did rational expressions on Tuesday, we looked at things that we could do. And the things that we could do would be simplify vertically or diagonally. And if nothing did that, we just multiplied straight across. Okay, so looking vertically, well, this one has an M up top and an N on the bottom. So those don't do anything to each other because they're different bases. This one has an M on the top and an N on the bottom, and they don't do anything to each other. So vertically, neither of them do anything. And then we go diagonally, and they don't do anything either, because 25 is not divisible by 2, so I can't cancel anything there. N doesn't go into M. That doesn't work. Same way with the other diagonal. So nothing simplifies vertically or diagonally with this one, which is fine. It's not a big deal, because now all I got to do is just multiply straight across. Top times top, bottom times bottom. So the top, pretty easy. You got 25 times 1 is 25. And then since I'm multiplying, these two have the same base, so I can add them together. 8/3 plus 4/3. So I'm going to get a little help here. 8 over 3 plus 4 over 3 would be 12 over 3, which is the same as 4. So that ends up being m to the 4th power. Hey, I didn't even have a fraction exponent on that. That's nice. On the bottom part, same thing. Got a 1 in front of that n. The 1 times 2 is 2. And then n to the 4/3 times n to the 5/3. Those are the same base, the n's. So I can add the exponents. 4/3 plus 5/3, which would be n to the 9/3, which 9 over 3 is 3. 4 over 3 plus 5 over 3, 3. And I'm done. I've simplified as far as it'll go. Happen to get rid of all my rational exponents. That's not a necessity that you do that. You don't have to get rid of rational exponents. If there are negative exponents, then you do need to fix those and make them positive. All your answers should have positive exponents on them, not no negative exponents out of that. So, but just simplify as far as you can, one step at a time. All right. Let's look at another problem that asks us to simplify. Oh. All right. Let's say we had y to the 3/7 parentheses y to the 4/7 minus 5 y to the 11/7. So that looks a lot like this problem. That kind of problem over here on the right, what property is that? It's distributive property. It's the same thing over here, even though it's got those wacky fraction exponents. It's the same problem. On this problem, you just distribute. The same thing happens here. You're going to distribute this and multiply it to both of those pieces. Okay? You're not distributing the exponent, you're distributing the whole piece. So what that ends up doing is saying, okay, I got y to the 3/7 times y to the 4/7 minus y to the 3/7 times 5 y to the 11/7. So that's what we're doing. We're distributing that whole y to the 3/7 to both of those terms, because it's separated by a minus sign there. So leave that minus sign in the middle. And then we just follow the rules from there. We say, okay, they're multiplying y to an exponent times y to an exponent. So the bases are the same. So that means I can add those exponents. So 3 plus 4 on the top would be 7. So that's y to the first. 3/7 plus 4/7 is 1. And then on the second one, we got this 5 and that's kind of making it a little tougher. So we got to take care of that. Well, it's really 1 times 5, which is 5. And then we have 3/7 plus 11/7. Maybe I'm not as good at that. And 11 plus 3 is 14. 14 divided by 7 is 2. It ends up working out to be y squared there. And this would be an acceptable answer. Normally, because it turned out to be a polynomial, we would write it in this order. Either of those would work fine. I'm not going to be too picky about those. Just understand, if this, on the multiple choice part of the Canvas quizzes, if this is not an option, look for the other way rearranged version of it, because they just put it in descending order out of that. So working with those exponent rules and the rational exponents really is a big deal as far as simplifying things and going from there. All right. Let's go to the next section, which is almost the same stuff. I mean, it really is. They call it something different, but it's very, very similar. And we actually can turn any problem in this section into one from the last section. I probably said this before, that the trick with most mathematicians is the fact that they don't know a whole lot, but they know how to take things that they see and turn them into things they know a lot about. So that's what R7 does, is it takes radical expressions and we take those and we can turn those in to rational exponents. So that's the trick we're going to use to help us here. Okay, and radical expressions are like this. We have an index, and then you got some sort of base inside, and we'll put an A there. That if we have a radical expression, this index here is what root we're doing. So if it's a square root, that's a 2. They never write it there, but it's a 2. If it's a cubed root, there's a 3 right there. And this exponent here is on the base B. You can convert any radical expression into a rational exponent expression by taking it and using the same base. So the base is B, and our fraction becomes A over N. Whatever exponent is here goes up top, and then the index of the root, whatever root you're taking, becomes the denominator. That's the trick to converting from a radical expression into a rational exponent. And one of the things it does is just, if it's a number that'll work out with the calculator, makes it faster to type into the calculator, because the indexed root is in a menu and you got to go hunt it down. Rational exponents we can type in straight away, but it also helps us in the fact that, hey, we can convert something over and do all those exponent rules that we know all about. There aren't very many rules listed out for dealing with radicals, but there are all those rules for exponents that we already know. So what we can do is convert and then use exponent rules. And then if they want the answer in radical form, we can convert back at the end and get a nice looking answer in radical form if that's what they want. So let's look at a few of these. We'll do some that work out nice, and then we'll throw some variables in there and try to and convert back and forth between our different versions. So I got we're going to hit the whole alphabet in this section just to get a lot of practice with this, because it's a good thing. All right, so start with this one. A is the cubed root of 27. And I'm going to show you how to get the indexed root with your calculator. I believe I've showed you how to get the cubed root, but I want to show you how to use an indexed root with the graphic calculator, and then we'll do a rational exponent as well form. You can do this one with the calculator. It works out real nice. To get that indexed root, you go to the math menu. So it's right third one down from the right underneath the green one, and then if it was a cubed root, you can use a straight up cubed root. The option 4 gets you a cubed root. And, you type in 27 and it should be 3. That's what's going to be the answer. If it's a different root, like a 4th root or a 5th root or a 7/8 root, something weird out of that, you can hit math and then go down to option 5 that has that X with the square root symbol out of that. What that does is it allows you to type in what root you want to take. So if I can type in a third root of 27, it's going to give me the same answer out of that. So that's how you can use that with the individual root with the calculator, which is helpful when it's good numbers and it works out nice. Not so helpful when it's variables, and that's where the rational exponent idea comes back out of that. So let's, if we convert this in, we know the answer is 3, and we'll put that there. What I want to kind of do as we go along is think, okay, this is actually 27 to the first power, so that ends up being 27 to the 1/3 power as a rational exponent. So we're going to convert these as we go, just so that we can be really good at that once we get to needing that. Okay, and then if you did in the calculator 27 raised to the 1/3, it's the same answer. It's a beautiful part of it is it's the same answer no matter which way you do that. So maybe too many options could get a little tougher, but 4th root of 10,000 is a good number. So 4th root of 10,000. Again, with the calculator, you could hit math and go down to option 5 and put a 4th root of 10,000, and it should give you 10. That's nice, but it's not the only way to do that. You could also think about this as 10,000 to the 1/4 power and work that out as well. I also know that 10,000 is 10 to the 4th, and that's 10. That works the same way. So doing these as rational exponents, it opens up the idea of doing it by hand, which is, I think, helpful when we start going to equations and being able to convert some things over to the same base and things. It really does help a lot. Where they can throw you a little bit of a curveball is throwing a negative number in there. And again, if it's a negative number that's inside of the root, you got to look at the index to decide if you'll have a real solution. If it were the square root of -216, we know that that's a complex, right? But if it's the cubed root, then we know we can get an answer. If it were a 4th root, you would say that's a complex solution. We're not going to get that. Okay, so be careful of that. If it's an even index on the root, it's a complex solution. That's the key. And it goes back to that rule that we talked about when we were talking about rational exponents. But this is -216 to the 1/3 power. That works here, and I actually think we did -216 to the 1/3 earlier. We didn't. Negative. Oops, I'm gonna put cubed root. So math or -216 should be -6. -6. And if you did that with the factor tree, it works out same idea there. Very very nice out of that. But knowing the rational conversion from that is very handy. Let's throw a fraction in there. So the cubed root of 125 over 512. So this one is it's a fraction inside of a radical. And anytime you have a fraction inside of a radical, one of the things that you want to try, you would look to do would be simplify the fraction. So check to see if 125 over 512 will simplify. Because sometimes they'll throw one at you, and if you'd simplify it, this one doesn't, then sometimes it'll work out easier if you simplify. This one doesn't simplify, so that means we're going to have to work it as is. And the way to do that is to convert it over to the cubed root of the top and then the cubed root of the bottom. So it doesn't matter what root it is, if it's the fourth root or fifth root, the same rule applies. Just split it apart and do the same root on each one. Okay, and then I'll type in the cubed root of 125 should be 5, and then the cubed root of 512 should be 8. 5 over 8 is what it reduces to out of that, which is nice. And again, you could do that with the rational exponents. You could convert that to 125 over 512 to the 1/3 power, or if you work this out, it's 5 to the 3rd over 8 to the 3rd, which is actually 2 to the 9th. All of that to the 1/3 power. That a lot of different ways to get the same answer there. I like doing the different bases and things just to get me some practice with that, because I know I'm going to need it later on with that stuff. All right, let's do example E, which is we're changing up directions. We're not simplifying here. We're just converting. So we're just going to work on the conversion. So we're going to write each rational exponent as a radical expression. All right, so we're taking a fraction exponent like this one, 16 to the 3/4, and we're going to rewrite it as a radical expression. So if the whatever the denominator is, that becomes the root you're taking, always. Okay, so fourth root, and then we have 16 to the 3rd power on the inside, and then the numerator again becomes your exponent on the inside. So 16 to the 3/4 becomes the 4th root of 16 to the 3rd. That's what we're trying to do here, is just work on the conversion back and forth. Example F, x to the 5/6, or an x as a base. What root would it be? What's the index of the root? 6. Whatever the denominator is, it's going to be that index that's on the outside every time. And then be x to the 5th on the inside. Seven x to the 4/5. Rewrite that fraction there. There we go. This one, it's a little bit, they put a little spin on the ball on this one, because that 7's in there. What part of it has the fraction exponent? Just the x. So this part is the only part that ends up underneath a radical. The 7 just hangs out in the front. And then you do the radical with the x. So that's where they kind of put a little spin on it, make it tough. All right. Now that'd be the 5th root and x to the 4th power. fifth root x to the fourth power. Again, the 7 has to be out in the front for that to be correct. 7 on the inside would be incorrect on that problem. So be careful of that. They can be tricky. Here's another one. Maybe this one's got a little bit more spin on it because it's got parentheses in it. What do you mean? You could. I probably wouldn't, just because it's not going to change it any. I would look at it and say, okay, well, what's the index on the root? 8. And when I distribute that out, both of them going to have that same denominator, right? So that's why I wouldn't do it. If there were an exponent on one of those that might change that, maybe I would, but most of the time you're not going. You don't need to. If you'll just work with it from there. So what would go on the inside here? Be 5x to the 7th, right? So that whole thing in parentheses raised to the 7th power. That's one way to write the answer. It would also be correct to have the 8th root of 5 to the 7th x to the 7th, which would kind of be, Courtney, like what you were saying. If you went ahead and distributed that out and had 5 to the 7/8 and x to the 7/8, then yeah, it's the same thing. But those are equivalent expressions, and I actually think this one is the one that you'll see most from this particular textbook and testing format for this class. How that? There's Miss West, I believe. All right. Let's go the other direction. Let's take from a rational exponent or from a radical and then convert it into a rational exponent and see if we can go that direction on this. So write as a rational exponent. Writing as a rational exponent. So we're going to get a radical in our original problem, and then we're going to go from there. So let's say we had the 7th root of n to the 3rd. So we'll just use a fraction or a variable here at the beginning, and then we'll throw some. It's got everything in it. So 7th root of n to the 3rd. So that'd be n is our base. What's our exponent? 3/7. Remember that index that's out there becomes the denominator. The exponent that's on the inside becomes the numerator of the fraction. It really just a conversion. We're not really working anything out here, just converting. Say we had the 4th root of 10x. Do an x there. There's a couple of different ways to write this one, but either I think they're both equivalent, but I'll show you which one I think is the most common way. So again, your index becomes the denominator, and then what's the exponent? So that could be 10x raised to the what over 4? 1/4, yeah. This would be one way to write it, and I think that's the most common way that you're going to see it. But you could also have 10 to the 1/4 times x to the 1/4. Those are the same problem, and it goes back to that exponent rule idea that this boxed in thing, we really have a 1 and a 1 there, and you could distribute that exponent, but it's not necessary, I don't think. I think the one that's boxed in is the most common one, but understand that they are the same. They're equivalent expressions out of it. Okay. So index on the outside, and then since both of those didn't have an exponent written, they had ones that are understood to be there. That's the key to that. Let's do this one that's got 15 and then 7th root of x to the 4th. 7 right there. So 15, 7th root of x to the 4th. So is the 15, is it going to have a fraction exponent? No, because it's on the outside, right? It doesn't even have any, it's just hanging out, watching what's happening. So this part is the only part that's going to convert over into a fraction exponent. So it'd be x to the 4/7, and then the 15 is just in front, multiplying times it. There's one they kind of, a little bit of a change up on you there when they put those numbers out in the front. Can really mess with you. One more conversion that direction. Let's go -2 5th root parentheses 3x squared to the 8th. So this one's got a lot of stuff happening in it. It looks real busy, but it's really, if you just think about it in the simplest way possible, and then think exponent rules, it's a little easier. It looks like it's got a lot going on, but here's the thing: you got a 5th root. That 5th root is only on that stuff. And if you'll think about this, the 3x squared as being your base, you're going to have -2 times 3x squared to what power? 8/5, yeah. 8 is the numerator. 5, remember that index there is always going to be your denominator out of that. So that's one way to write that answer. I think this one they would actually work out a little further because it's got these exponents in here that you could do something with. That you could convert that out to be -2 times 3 to the 8/5, and then x to the 2 times 8/5, which would be 16/5. I think that one they would do because of the x squared there. That's the reason that they would go ahead and go a little further with that one. But on labs, if you got one like that on labs, I would take the first one too. It'd be correct. It's correct. You did what I was asking you to do. You converted it out of a radical. But I really, honestly, I think this is the one like you're going to see more of in that goes. All right. All right, let's look at what if it's an even index of a variable, and what we've got to kind of keep in mind here. Even indexes, when we took square roots in problems, a lot of times, if we put a square root in a problem to solve it, we had to do that plus or minus in front of it. When we were doing quadratic formula, we always had that plus and minus because it was a square root. So if it's an even index, when you're dealing with these things and you're simplifying, so we're going to simplify an expression, we've got to watch for the ones that have an even index. If it has an even index, then we've got to worry about pluses and minuses, and then of variables, we got to worry about absolute value marks, and I'm going to show you when that happens. Okay, so we'll start with this one. We'll start with the 4th root of x to the 8th. That's one that works out real nice. If we think about that as a rational exponent, it makes it a little easier than doing as a 4th root if we're going to simplify that. Because 4th root of x to the 8th, we don't know what x is. It's not a number, right? So we can't do anything, we definitely can't type that in the calculator. So if we think about it in terms of a rational exponent, it becomes x to what power? 8 over 4, right? And then the 8 divided by 4 simplifies, right? It becomes x squared, right? And because we had an even index, we need to put absolute value marks around that because it divided out evenly and it was an even index. If it was an odd index, absolute value marks don't happen with odd indexes at all, because odd indexes are third powers. You can have negative answers in those. With even indexes, we can't have negative numbers in there. So we need to guarantee that that's going to be a positive number. What guarantees positive answers? Absolute values guarantee positive answers. So that's where that's going to come in there. Okay. We're always going to have absolute value marks on that. Okay. If it's an even index and it simplifies out nice like that. Here's an example of one that's an odd index. Maybe it's something like the third root of n to the 12, something like that. And here, that's gonna, you think about it as a converting from a radical expression into a rational exponent. So index is 3, so that becomes the denominator. Whatever exponent's here is the numerator. And then we simplify if possible. 12 divided by 3 goes evenly. Fourth power. We don't have to put absolute value marks on that because it was an odd index. Okay, so you won't see absolute value marks on that because it's an odd index. Okay. Another one. Let's do this. There's a good one. Kind of throws in some stuff that we might accidentally forget. And no, I didn't forget to write something. What do we know about that particular root? If nothing is written up here, what's really there? Not a 1. What symbol is that? When it doesn't have anything written there, it's what kind of root? It's a square root. So it's really it's a understood 2 that's there, which seems weird because everywhere else in math we say it's a 1 understood to be there. But when we're dealing with radicals, it's understood that the least radical that you're ever going to do is a square root. So it's understood to be a 2 there if nothing is written. So when we work that out, we know that that's x to the 6 over 2. 6 divided by 2 ends up being x to the third. And we need absolute value marks on that? Yes, because it was an even index. So absolute value of x to the third. In which there are times where absolute values would be redundant because if the exponent ends up being even there, it automatically becomes positive no matter what you put in there. But I like to have them there just as a reminder that an even index is always going to have those going on. Let's look at one that puts a little bit more stuff underneath the radical, and we're trying to simplify here. So square root of 81 x to the 8th y to the 10th. And this one is one of those that can one part would have to have absolute values, another part doesn't have to have it. So what do we know about the square root of 81? Do we know that? It'd be 9, right? 9 times 9 is 81. So the square root of 81, we can go ahead and simplify. If we didn't know, if that wasn't 81, say that was like a number like 48 or something that doesn't have a nice square root, we could simplify that with the factor tree or some other method to get there. This one works out nice. Most of them they give you in this section do work out pretty nice. So then we work on the x and the y. So we have x to the 8th, but it's under a square root, so that's x to the 8 over 2 and y to the 10 over 2. And then we simplify those. 8 over 2 becomes x to the 4th. 10 over 2 becomes y to the 5th. Technically, both of those would have absolute value marks around them. But you probably will not see absolute value marks around the x, but only of the y, because anything raised to the 4th power, no matter, if I take a negative number, let's say I take, for example, -2 and raise it to the 4th power, it automatically turns positive. So that's why you don't have to have those there. The y being to the 5th power, well, what if y were -3? -3 raised to the 5th power is a negative number. So yeah, I do need the absolute value marks on it. So a lot of times, some textbooks, you will see them already go ahead and put the absolute value marks on that piece. This particular textbook doesn't on those problems when it works out nice and it's an even answer on the exponent. On the lab, I'm good either way. Understand that on the multiple choice, you may or may not have that. You won't have the absolute value marks on there if it doesn't need them per se. Okay, so you gotta kind of be careful about that. Let's do one with a number in it that actually can work out, and we'll do it through rational exponents, and then I'll show you with the calculator doing it as well. So. So we had 4th root. So there's an even index of a negative number, but I'm going to raise it to the 12th power, so it's not negative anymore, really. So it looks like, oh, you can't have a real answer with that. But because the exponent on the inside is even, it makes it work out okay. So if we did this with rational exponents, like we've been doing all these with the variables, it works out real nice. We get -3 raised to the 12 over 4, which is really -3 to the 3rd power. But because it's an even index, right? And then -3 to the 3rd power is -27. That's 27. Absolute value of -27 is 27. That's kind of nice. Pretty neat how it works through the exponent rules and then those rules for that even index. If I did this with the calculator, I could hit math, and then I could go down to that option 5 and put a 4th root, and then parentheses -3 raised to the 12th, like that. And it cranks out the same answer out of that. So when it's a number in there, yeah, you get the niceties of being able to type that in the calculator. Whether you want to use the root with the index, or if you just typed in -3 raised to the 12 over 4, using that rational exponent. Now, here's where the not using the root comes back. You got to remember, oh, it's an even index, and I've got to do the absolute value at the end. That's the calculator. When you do it as an exponent, it forgets that rule because it thinks, oh, this is just an exponent problem. It doesn't know that it came from a indexed root problem. So you got to be careful about that. And some folks get in the habit of going ahead and doing it this way, which is fine, but you got to keep that one little tiny rule in mind. There's always those little details that can mess us up. So you got to be careful about that. But since they've upgraded these graphing calculators in the last 6 or 7 years since I've been teaching, they used to you didn't have this option to do the 4th root. So you guys are living in a good time because it works out real nice for you and does a lot of stuff for you. I remember learning this in high school or in college algebra in college, and it was there wasn't as nice of calculators out there then, and you couldn't afford them. So you just had to learn to do it the other way. So let's look at one. It's just a fairly simple variable problem. Got a couple of variables in there. Fifth root, m to the 10th, n to the 15th. Nothing just crazy there. Again, I think, you just convert m to the 10 over 5, n to the 15 over 5. Get the same, the index becomes the denominator. And then simplify if possible. If it doesn't simplify out, then just leave it as the fraction. Just reduce your fraction as much as you can. So here, 10 over 5 works out to be m squared. 15 over 5 is 3. Do I need absolute value marks on those? Why or why not? It's not an even index, so I don't need absolute value marks. Remember, odd index, I'm never going to need absolute value marks. Only on even indexes do I even have to think about that. So I'm just going to, that's it. That's the answer on that one. Okay. This one's a little weird. It looks strange, but it's not that difficult. Let's say we had something like the cube root, and then they put this weird polynomial thing in here. And it looks like, oh gosh, that's the hardest problem that they could give us, because they have 3x minus 4 raised to the 6th power. And I've had students in the past that thought, oh, I've got to multiply that all out and then do my root. But no, remember, on the rules with order of operations, what comes first? Parentheses and then exponents. Well, if I go inside of the parentheses, I can't do anything with 3x minus 4. And then exponents happens next. Well, we're smart enough, and we've been learning today that in the third root is the same, the cubed root is the same thing as a 1/3 power. So it's really an exponent. So if I do this with exponent rules, that becomes 3x minus 4 to the 6 over 3. And whoa, that works out a little nicer. That's 3x minus 4 squared. Technically, do I need, or not technically at all, do I need absolute value marks on that? No, I got an odd index, right? Odd index says I don't need absolute value marks. Can I multiply that out? Yeah, you could. You could multiply out 3x minus 4 squared. That would be 3x minus 4 times 3x minus 4. You might see this as an answer, but you could end up having to multiply it out. It just depends on the problem. And then you should multiply it out to 9x squared minus 12x minus 12x plus 16. Simplify that just a little bit more. Get the like terms in the middle. And we get 9x squared minus 24x plus 16. Either of those boxed ends, they're equivalent solutions, but just one's multiplied out and one is not. So looked like it was going to be difficult. Turns out it works out real nice. So anytime they throw you one, it looks like it's just going to be outrageous in this particular section. It's usually not. If you'll go through exponent rules, it's probably going to work out real nice for you out of that. All right. Now, here's another one that looks real hard, but if we'll think a little bit, it doesn't. It's got some shortcut to it. And that's where they put like a square root. So we're using a square root here. And let's do x squared minus 10x plus 25 in there. So they put a polynomial inside of that square root. And we got to just kind of remember some context of what's going on here and where we're at as far as the material we're studying. So anytime they throw that at us and they say, okay, well, simplify that. This x squared is tied to all this other stuff with addition and subtraction. So you just can't take the square root of x squared. You've got x squared minus 10x plus 25 in there. So what we think about doing is converting this into looking something like that problem did. So to get it to look like that, it would take factoring of this trinomial. So I'm going to try the x method of factoring on that trinomial. Multiply to be 25, add to be negative 10. That would be negative 5 and negative 5. So this really factors as x minus 5 and x minus 5. What's another way to write x minus 5 times x minus 5? Yeah, and that's the trick, is making it look like something else. Part of being the algebra stuff. And now we can work that out a little bit better because this is a square root, so the index is a 2. So it ends up being x minus 5 to the 2 over 2, which simplifies to be x minus 5 to the first power. And technically, it should have what on it? Absolute value marks. Why does it have absolute value marks? Even. That index up there is an even index. So that's why we need it. Anytime it's an even index, that's what we need. All right. All right, let's look at simplifying some expressions that have multiple radicals in them. So we've been simplifying single radicals here. So let's do some that multiply some radicals together or divide them, or maybe they have radicals inside of radicals, which makes them look tough, but we know that anything that looks tough can be changed into something that's not so bad. All right, so that's what we're going to try to do here. All right. Simplify. All right. The square root of 5 times the square root of 45. So, if we remember from 100 when we were doing some stuff with square roots, any roots, the rules are when you multiply, it's outside times outside, inside times insides. And in order to multiply things together, they got to be the same root. So both of these are square roots. You're not going to get any that are mixed together usually. And the thing that I'll tell you is it's better to simplify last. Don't try to simplify at the beginning, because square root of 45 will simplify, but I don't think it helps you to simplify it now. It'll help you more to simplify at the end. So let's do the math of multiplying them together first, and then we'll do something with what's left. Okay, so if I multiply these together, I actually end up with 5 times 45. So I'm just showing that step that I'm multiplying inside times inside. If there were numbers out here besides 1, I'd say, if this was 3 radical 5 times 4 radical 45, I'd say 3 times 4 on the outside. So it's outside times outside, inside times inside. That same rule applies even if it's cubed roots or 27th roots. It doesn't matter. It's the same rule. Okay? And then if we want to multiply that number together, we can. 5 times 45, 225. So that ends up being the square root of 225. And then we could simplify that. The number 225 kind of rings the bell with me, so I'm going to check it to see if it's got a square root. The second square root of 225. It does. It's 15. If it did not have a nice square root, I would take that and do the factor tree stuff with it. If it were some other number, we'll do. Maybe we got this 3 radical 6 times 5 radical. Let's do 12. Okay. So there's one I know that doesn't simplify or doesn't have a nice square root. I know it's going to work out. So rules are outside times outside, inside times inside. So we have 3 times 5 on the outside, 6 times 12 on the inside. That's what we're doing with that problem. We're going to get those numbers. That'd be 15 square root of 6 times 12 is 72. And then 72 doesn't have a nice square root. So that means I got to simplify this using factor tree or whatever other method that I might use. So 72, I got it from 6 times 12, so I'm going to use that. 3 and 2, 6 and 2, 3 and 2. So I got 2 pairs of 3s, and then a 2 that's left over. So I got 15 times 2 times 3, and then I got a 2 left over in there. So I need to multiply all this stuff out on the outside. 15 times 2 times 3, 90. End up with 90 square root 2. Not a lot of rational exponent stuff here, just because we're dealing with regular numbers. If we were dealing with variables, then I think that the radical or converting that into an rational exponent problem does work out nice. Let's look at one that's got variables in it so that we can do that. Say we had the 5th root of n to the 6th times the 5th root of n to the 4th. Okay. Rules are outside times outside, inside times inside. I can multiply these two together because they are the same root. They're both 5th roots. So that makes it legal to multiply them together. So when I do that, I'm going to have a big 5th root of n to the 6th times n to the 4th. This is where we get into using those exponent rules that we've done. They have the same base. So what's the rule when I multiply with the exponents? I'm going to add them up. So 6 plus 4 would be n to the 10th. And this is where the taking it from a radical into a rational exponent is key. Okay, so here we got an n to the 10th inside of a 5th root. That's really n to the 10 over 5, which ends up being n squared. Do I need the absolute value marks? No. Odd index, right? So I know right at the beginning, I already knew I didn't need absolute value marks there. There's taking something and adding a little bit to it from what we've done before. Okay. We did one like this earlier with numbers. Let's do one with letters. Let's do the 6th root of a over b to the 12th. And let's see if we can simplify that a little bit. Remember your rules. Your rules say if it's a root and a fraction inside and the fraction won't simplify, split it apart to where it's that same indexed root on top and bottom. And then work those separately. Well, anytime it's a variable in a root there, I'm going to convert that over. A to the 1/6 is going to be b to the 12 over 6 and see if it'll simplify some. Well, the a to the 1/6 doesn't work out anyway. It doesn't do anything. But the 12 over 6 does. It ends up being b squared. And a to the 1/6 up there. Now, this is one of those cases where do I need absolute value marks on the b squared? Technically, yes. But if I square something no matter what I square, what's it always going to end up being? Positive anyway. So that this will be one of those cases where technically, yes, there should be absolute value marks around there, but they're redundant because anytime I square something, it's always going to be positive anyway. So no matter what B ends up is, if they tell me B is negative 752, if I square negative 752, it still turns into a big positive number. So it's technically there should be absolute value marks there, but you don't have to have them there. And this is one way to write the answer. Another way would be if they converted it back to a radical. Only one of those converts back. It's that top one. It's the sixth root of A over B squared. This is, an alternative answer that's the same thing. Okay, so sometimes they convert them back, sometimes they don't. This particular textbook seems to go either way with that. They're not as consistent on that as I would like for them to be. Okay, so split it apart. Anytime it's a fraction inside, split it apart, and that's going to help you get the individual pieces and simplify the top part and then the bottom part, and then see if there's anything you can do there. Okay, so there's a fraction on the inside. Let's look at a root inside of a root. For example, y is going to be the fifth root of the fourth root of 17. And we're just going to try to rewrite this as a rational exponent. That's what we want to do here, because it's not going to work out to be a nice number. So we're going to get the idea of rewriting this as a rational exponent. I'll tell you what, change that 17 just to an x. That makes it a little easier to think about here. Sometimes we put a number in there, we get a little sideways about that. So let's work that out. All right, so anytime they got a more than one radical in there, you want to start on the furthest one on the inside and think about, it's kind of like if you were trapped inside of an apple, how would you get out? You'd go from the inside out, right? So that's what you got to do here. So if you'd ever been trapped in an apple, you might have that dream tonight. I'm not sure. So we're going to start on the inside there. So we're going to convert the fourth root of x into x to what power? Be the 1/4, right? Because the exponent on the x is a 1, and the index on that part is a 4. So now we've got this new problem. We've got the fifth root of x to the 1/4 power. And then we can convert that into a rational exponent, because whatever's in here is going to be raised to what power? X to the 1/4 will then be raised to the 1/5 power, because a fifth root is the same as a 1/5 power. What's the exponent rule when that's with those? Parentheses with an exponent outside says multiply. So that's going to be 1 times 1 would be 1. 4 times 5 would be 20. X to the 1/20th. We'll do another one of these. This is looking at me like a calf staring at a new gate. It's weird. Don't get me wrong. I know it is. It's just you got to start on the inside. So let's take this. Do another one. Same idea. Let's do x squared on the inside this time though, just so it's got a little difference in it. Okay. So start on the inside. So we're going to convert this one into being x to the power. 2 over 6. And then that's still underneath the square root. I'm going to go ahead and put another step in there because we know 2 over 6 is really 1/3, right? So I'm just all I did from step 1 to step 2 was change the 2/6 to 1/3. Just reduce that fraction because it would. Now, next thing to do would be to convert this into from a radical into a rational exponent. So be x to the 1/3 power raised to what power? 1/2. Yeah, because it's a square root. It's got an index of 2, so that's a 1/2 power. And then the rule is, parentheses, exponent on the outside, multiply them together. 1/6. Good job. That's it. Well, it's not quite as bad as it looks. It just, you gotta start on the inside and just kind of ease your way out. We'll do one more and see how we do. We'll call this example double A. Got past the whole alphabet here. Make one up here. Let's do the cubed root of the 4th root of the square root of x. So 3 radicals in there. If we can wrap our head around that. So again, you're going to start on the inside. What does that one become? X to the 1/2. Good. And then we still got the 4th root and the cubed root. So now this is going to become x to the 1/2 to the 1 over what? 1 over 4. And then we still got the cubed root there. Well, I'm going to go ahead, and because I know I can simplify that, I can go ahead and do that. So it's going to be the cubed root of x to the 1 over 8. And I've got to do the next step too. So just simplifying as I go here. And then from there, I'm going to take the x to the 1/8 and raise it to what power? 1 over 3. Yeah, 1/3. And then multiply that out, and I'm done finally. 1 times 1 is 1. 3 times 8 is 24. I don't think you'll see one that has 3 in it, but the logic that it takes to get out of 3 of them is the same as it takes to get out of 2 of them. It's not, if there were 5 of them, it's the same logic. You start on the inside and just kind of step one step out of the building at a time. That's all you got to do there. All right. So that gets us to the 3rd section for the evening. Let's take a little break, and then we'll come back and get this last section. This last section is about solving equations, so it's kind of different than the first 2 that we've talked about. It's solving equations, so it's going to be a little different. So let's take a little break,